Okay, so let's continue with the example that we were just looking at, where we had a sample of 4 observations, x1, 2, and 3, and 4, which were assumed to have been pulled from a population which is distributed by the Poisson distribution. But we don't know what the parameter lambda is in that Poisson distribution. So what I'd like to do now is say, well, given that we've observed this sample over here, what value of lambda is the most likely value? So I want to take this probability, and now I'm going to think about it as a function of lambda. So I'm going to call this function L for now. We'll see why it gets called L. But I'm going to think about L as a function of this parameter lambda, given that we know our sample x1 was 1, x2 was 3, x3 was 4, and x4 was equal to 8. So this is our given information. And so what we'd like to say is, given these 4 values that we've observed, what value of lambda is going to be most likely? And what we know is, well, this is the probability of getting that output. So I'm going to condense this formula. For example, I have lambda to the first, lambda to the third, lambda to the fourth, lambda to the 8. So altogether, that gives me lambda to the 16 on top. And I have e to the minus 4 lambda, right? Because I have 4 of those terms. So if I were to multiply this times that, that gives me e to the minus lambda minus lambda minus lambda minus lambda. In other words, e to the minus 4 lambda. And then we're going to divide all of that by 1 factorial times 3 factorial times 4 factorial times 8 factorial. And so now what I'd like to think about is, okay, now what I have is a function L. Okay, and what this function is telling me is, given a value of lambda, this is how likely it is to observe an output of 1, 3, 4, and 8. So this is what's called the likelihood function. So let's define this more generally up here. And so the likelihood function is, now this is a function of the parameter. In this case, theta is denoting some arbitrary parameter. So the likelihood function gives the likelihood of the parameter theta given the observed data that we have. And so a maximum likelihood estimate, and we're going to denote maximum likelihood estimate with an MLE, is the value of theta that maximizes the likelihood function. So if I were to plot this graph, so if I were to graph this function over here, notice now that this function that we've graphed has lambda as the input, and the output is the value of this likelihood function. Okay, the output is saying, what's the probability of getting the sample that you've observed? And what we want to do is, we're going to pick a value of lambda that makes it most likely that we would have observed our data. And for this case, it seems to be that when lambda is equal to 4, we have got the biggest value of this likelihood function. So looking at this graphically, we might say that my maximum likelihood estimate for lambda in this case is going to be 4. And so again, what the significance of this 4 is saying, it's saying that, well, here's the probability of getting our output. We don't know what lambda is, but if I set lambda equal to 4, that's going to make this probability greatest. So we're finding the value of the parameter that maximizes the likelihood of getting the observed sample that we've gotten. So this is just a quick, maybe not so quick, but this is an overview of what's going to happen in the first section in Chapter 6. So let's walk slowly through a couple of examples and see how we can come up with a step-by-step process for finding maximum likelihood estimates.